Welcome to Dr. Sherry's Astronomy channel. The topic of this episode is the discovery of the most distant blazar. A blazar is a celestial object powered by a supermassive black hole, characterized particularly by its powerful relativistic jets. Because it contains a supermassive black hole, it is considered a similar type of object to quasars. When a supermassive black hole consumes matter, an accretion disk forms, and gas or plasma is expelled as jets at nearly the speed of light. Depending on the angle at which these jets are observed, they appear as different celestial phenomena. When the jets are observed almost head-on, relativistic beaming effects enhance their brightness and energy, classifying the object as a blazar. Blazars are similar to gamma-ray bursts, as both release intense brightness and energy via relativistic jets. According to Einstein's theory of relativity, when an object moving at the speed of light emits light, a beaming effect occurs. For instance, if an observer moves alongside the celestial object, the light appears isotropic. However, if the object approaches the observer at the speed of light, all the emitted light converges into a narrow angle, as shown in this diagram. This means that light emitted in the opposite direction, normally invisible, becomes observable. As a result, light originally radiated in all directions appears focused and brighter to the observer. The angle of this beaming effect is defined using the Lorentz factor, which depends on the speed of the object, v, and the speed of light, c. Let's examine the magnitude of the beaming effect using the Lorentz factor. This diagram illustrates how light from an isotropically radiating object becomes beamed due to motion. The top shows the speed of the object as a fraction of the speed of light, and the Lorentz factor is indicated below. When the object is stationary, the Lorentz factor is 1, and light is distributed evenly. At 50% of the speed of light, the Lorentz factor is 1.16. At 90% and 99% of the speed of light, it becomes 2.29 and 7.1, respectively, concentrating radiation in one direction. At 99.9% of the speed of light, almost all the radiation becomes observable. Beaming not only brightens objects but also increases the observed energy of their light and compresses the timescale of observed phenomena. This makes beamed objects highly energetic and rapidly variable. For blazars, the required Lorentz factor is around 10, while for gamma-ray bursts, it exceeds 100. This indicates that light-emitting regions move at least 99% of the speed of light. Blazars in such extreme physical conditions are notable for emitting not only high-energy light but also neutrinos and cosmic rays. In 2017, an event synchronized with neutrino detection and the brightening of a blazar was observed. This confirmed that blazars are sources of neutrinos. In December 2024, a study published in Nature Astronomy announced the discovery of the most distant blazar to date. This object was discovered through observations using the Very Large Array Sky Survey, VLIS, a radio telescope. Blazars appear bright in radio wavelengths due to their relativistic jets, unlike stars or ordinary galaxies. Thus, surveying large areas of the sky with radio telescopes is effective for discovering distant blazars. In visible light surveys, stars and galaxies outshine such objects, making them harder to detect. In contrast, radio surveys highlight extreme objects like blazars, enabling efficient discovery. Dr. Eduardo Bañados and his team at the Max Planck Institute for Astronomy identified the most distant blazar by analyzing radio sources detected by VLIS. The team matched the radio sources with corresponding visible and infrared objects and measured their redshifts through spectral analysis. The spectrum of this most distant blazar is shown here. By identifying features such as hydrogen emission lines, the redshift was determined. The result revealed a redshift of 7, corresponding to a time about 750 million years after the Big Bang. Additionally, the spectral properties indicated that this object hosts a black hole with a mass 700 million times that of the Sun. Furthermore, the research team examined the variability in radio waves and the broad spectrum from radio to X-rays to confirm that this object possesses relativistic jets, identifying it as a blazar. The actual spectrum of the object is shown here. The horizontal axis represents frequency, while the vertical axis shows brightness. The measured data are represented in blue, and the typical spectrum of blazars in the nearby universe is shown in orange. The spectrum of the discovered object aligns very closely with the typical blazar spectrum, and additionally, bright X-rays have been observed. These features are consistent with the characteristics of typical blazars. The radio variability is shown in this graph, with time on the x-axis and brightness on the y-axis. Observations in two frequency bands reveal characteristic variability unique to blazars. These findings reveal that, just 750 million years after the Big Bang, a supermassive black hole 700 million times the Sun's mass was emitting powerful relativistic jets. This discovery offers vital clues for solving the mystery of rapid supermassive black hole formation in the early universe. The origin of the universe suggests that about 13.8 billion years ago, it began as a hot, dense fireball. As it expanded and cooled, diverse structures, including stars and galaxies, emerged. Initially, there were no stars or galaxies. These structures formed later, followed by the creation of black holes as massive stars ended their lives. Early black holes likely had masses comparable to stars, up to 1,000 times the Sun's mass. How these small black holes grew into giants like M87's 6.5 billion solar mass black hole remains a key question. Another possibility involves primordial black holes, directly formed in the dense early universe, bypassing stellar evolution. These could provide a starting point for the rapid growth of supermassive black holes. This diagram is a schematic representation of the growth of black holes. The horizontal axis represents the mass of black holes, while the vertical axis indicates redshift, which corresponds to the age of the universe. Moving to the right signifies increasing mass, and moving upward represents earlier times in the universe's history. The observed data and several theoretical models for black hole growth are plotted on the diagram. Quasars are located in the lower right portion. Recent observations by the James Webb Space Telescope have revealed massive black holes in the distant universe. The areas beyond the observational reach of the James Webb Space Telescope are marked with a blue hatched region. How black holes formed and grew to reach the enormous masses of objects like M87 remains a significant question, and several theoretical models have been proposed. Broadly, two possible types of black hole seeds are considered: mergers of smaller black holes and the accretion of surrounding material. The relative influence of these two processes is not yet well understood. However, the merging of black holes in the distant universe has been observed with the James Webb Space Telescope. On the other hand, the accretion process is represented on the diagram with labels like multiple times Eddington. The rate at which a black hole can consume material has a theoretical limit, called the Eddington limit. Growth curves based on this limit are plotted on the diagram. Typically, black hole growth is expected to proceed within this limit, but recent studies have identified instances of super Eddington accretion, where black holes grow rapidly under special conditions. For example, one of the curves is labeled 10 times Eddington. Such an intense process of accreting material naturally results in the ejection of powerful jets as a reaction. This suggests the formation of celestial objects like blazars. Therefore, the existence of the most distant blazar discovered in this study implies that extreme accretion exceeding the Eddington limit was a frequent occurrence in the distant universe. Blazars, in particular, can only be observed when their jets are directed almost head-on toward the observer. As introduced earlier, their brightness is significantly enhanced by relativistic beaming effects. However, this effect weakens dramatically with even slight changes in the angle at which the jet is observed. In other words,
if the direction of a blazar's jet shifts even slightly, its brightness diminishes substantially, and it may no longer be observable as a blazar. As a result, although only one such blazar has been discovered, it is believed that many celestial objects with similar characteristics exist. These objects are not observed as blazars on Earth because their jets do not happen to align with Earth's direction. In this case, the Lorentz factor has not been measured, so the specific value remains unknown. However, based on typical blazar models, it is estimated that 30 to 450 times more such objects may have existed 750 million years after the Big Bang compared to those currently observable. This discovery provides a critical clue to understanding the mechanisms behind the birth and growth of supermassive black holes in the early universe. It holds promise for uncovering further mysteries through future research. We look forward to the exciting developments ahead. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.